Okay, hello everyone. So what I said up there, if you can decipher my writing, is what are the limitations of work energy formulations, aka what is this virtual work that I keep referring about and why do we need it? Why do we employ it? So let's just remember what I covered in last lecture, and by say remember, you probably just watched this or you may have even not watched the lecture. The fundamental tenet of work energy, it's not even the fundamental tenet. We introduce work energy principles because they help us to quickly and easily determine displacements. So they help us determine nodal displacements, and the governing equation we use is that the sum of external work done is equal to the sum of internal energy. And so we came up with definitions for these two things. We said that the external work done by a single force, with a single force, then the work done, UE, would be equal to a half multiplied by whatever force we apply in some dimension, let's call it I, multiplied by the displacement of the structure in that direction. Okay, so because these are always going to have the same sign, we get UE out as a positive number always. Okay, and as I said, they're useful because they help us look at things in a scalar format. Work is always going to be a scalar. The internal energy, very similarly, we said that internal energy was equal to a half multiplied by the internal force in a member. Let's call that Fm actually. Let's say that's Fm multiplied by the change in length of that member. And so this is useful for us. Again, we remember that if we've got whatever our sign convention is, if our sign convention is that tension is positive, then extension will also be positive. So these two will both be positive, we'll get positive work. Conversely, the contraction will be a negative number, and that's got to be there if we've got a compressive force. So those will both be negative, and we get a positive number out. And if your sign convention was the opposite, you'll still end up with the same, that will end up with always getting a scalar out. And then this was useful because more often, well, what we're going to be trying to solve using these problems is this displacement here. That's not circled that very well. Highlighters don't work very well when I do this, so let's just circle this with a yellow. Okay, this is the thing that we often want to know. So rather than having to look at the geometry of the external structure and look at how nodes move and then sort of unpin joints, pin them back together, we can just work out all of the internal forces and then consequently the single direction extensions or contractions of members, multiply them together, multiply it by half, add it all up, and then divide it by whatever our external force is, divide it by half, and we get the external deflection. So this means that all of the information for the geometry is given by the way that the external force, which we've applied, relates to this internal force here. So all of the geometry we'll say it's been captured and so it's captured in the external force to internal forces methodology. So this is external. And then this is my internal forces. And remember, this is just going to be tensile or compressive forces. And we know how to do this. We know how to take this. We take a structure, we do a free body diagram, and then the method of joints. I'm trying to think of, I wanted to say do all this work for us, and I don't want to use that expression because that can be confusing with work energy. So we'll say the free body diagram and the method of joints do all this heavy lifting for us, we'll say. And what I mean by that is that they can encapsulate the relationship between external forces and how that then relates to internal forces, and consequently the relationship between external forces and internal strain energy. Okay, so internal forces, this is the output from the method of joints. And then it's a short step to take us to internal strain energy. So the output from this will be just an array of forces that we have inside each of those members. So once we've got these forces, if we want to turn them into extensions, which we need to have, we then get extensions from change in length of a member is equal to, let's say, dl of member n. Let's write that slightly clearer. My handwriting's terrible. We say the extension, change in length of member m, is equal to whatever the force is in member m multiplied by the length, the original length of member m, divided by the Young's modulus and its cross-sectional area. And once we've got that and we've got these forces, so that would be our Fm, or all of those forces, then the internal strain energy that we already know, Ui, is equal to a half multiplied by the internal force multiplied by the change in length of that member, so dlm. Okay, this would be for a single member. I should put a subscript m down there, really, lowercase m, and then the total Ui for m members that's an uppercase and that's a lowercase here. Is equal to a half. Okay, so I'm not overstating this, I'm just repeating how this methodology works because it's really quite an impressive thing to do. We've taken what could be an horrendous geometric problem, and that bit that I sort of went through with the dodgy sort of rave music over the top, that was the method of sort of unpinning joints and working out how much they extend and thereby how much each node moves for a really simple problem, and that was still a nightmare to do. And involved me remembering what's the cosine rule, the a squared equals b squared plus c squared minus 2bc cos a. I had to do that for every, and if we've got a body that's got lots and lots and lots of members, we'd have to do that for every single part and get every single internal angle. What we've done here is we've said that the method of joints, it's already done that work for us. It's related the external force to the internal force, and as a consequence we can work out the internal energy. And because we can then work out the internal energy due to some external force, we then know that when we add all of those internal energies up, that's got to be equal to the external energy, so the external force multiplied by whatever the displacement is multiplied by half. So the only unknown is that displacement. So that's super handy. That's incredible. We've shown that we can get the correct displacement for a simple structure when we use this method. So what are its limitations? Why, how do we go any further with this? Well, let's think about it. So there's a couple of really important limitations here that you might have already thought about. I'm going to go through them in order. I said that we were going to use the work energy principle. Well, I actually said we were going to use the virtual work method, which is an extension of the work energy principle. But we're going to be using it to help us with the force method. So let's think about what the force method involves. The force method helps us determine the internal forces in statically indeterminate structures. Well, it doesn't help us, it enables us to. So if we have a degree of indeterminacy of 1, we use the force method. And the methodology with the force method was basically, 1, pick a redundant support, or pick a redundant reaction. And this is if it's externally indeterminate. We're going to use this a little later for an internally indeterminate structure as well, but this, as I'm writing it, is for an externally indeterminate structure. Pick a redundant reaction, set it to 0. And we then look for how much the structure deflects in the direction of where that redundant reaction is. So hopefully some of you are saying, well, there's immediately a problem with this. We can't use work energy methods for it. But let's have a think about it. If we had a structure with originally 2 built-in supports and some external force on it, and we said, okay, to solve this, we can see here that we've got 4 reactions. 4 reactions that we would have on the structure, because we've got 2 built-ins, both would have a Y and an X force. So if we wanted to solve this with the force method in the way we did it earlier, we said, well, let's just set this one equal to 0. And then that's equivalent to replacing this built-in with a roller support. And the deflection that we wanted to know was this first one here. This would be delta x or delta bx, whatever we called it earlier. This deflection is the one we wanted to know. Now, our force, our external force is up here. So we could quite easily, using work energy principles, work out this displacement, but we can't work out this displacement because we haven't got a force applied here. So using work energy methods as they've been described to us so far, we cannot solve the very first step of the force method. So we can determine the displacement here. There's no force, therefore no external work is done through this displacement. When it comes time to do the second displacement, when we set this equal to 1, we could very easily then use work energy principles. Our force would be 1, and we could work out that second displacement. But this very first one, we currently can't do. Okay, so it doesn't help us with that. It doesn't help us with that problem. Let's think about another limitation. Say I've got structure that looks like this. And let's say we've got two loadings on it. We've got P1 and P2. And let's say we've already gone through and we know the external reactions as a function of P1 and P2. So we've done the force method somehow. We've managed to do that. We now know the relationship between external forces and these internal reactions. Now, this structure under these two loadings is probably going to deform to look something like, that should be a straight line. Let's pretend I've drawn a straight line. It's going to look something like that. So we've got two displacements here that are associated with virtual external work. So we've got this displacement here. Let's call this delta 2, and that's the horizontal displacement of this node. So it's the displacement in the same line of action of that force. And then we've got this second displacement here. Or really, this should be first and second, doesn't matter. We've got two displacements, delta 1 and delta 2, P1 and P2. And I said that we could simply write the sum of external work done will be equal to this external work plus this external work. So the sum of external work for this would be a half multiplied by P1 multiplied by delta 1 plus P2 multiplied by delta 2. And if we have the relationship between P1 and P2 and the reactions, and we can do the method of joints to work out the internal forces, we would then we will be able to determine the internal energy. So let's say we've got UI. So we could work this number out, and we could then say it's equal to the sum of the external work done. Problem again, we can't determine this because we've got two unknowns and one equation. So this is known, P1 and P2 would be known, but the two deltas wouldn't be known. So in cases where we have two external deflections, we have too many unknowns and not enough equations. So the unknowns here would be delta 1 and delta 2. This equation is still true. Remember, this would be known because this would just be equal to the sum of the internal forces multiplied by the change in length of all of the members multiplied by a half. So we could get this as long as we've got the free body diagram method of joints and we've done that properly. We could get that. We couldn't get these two deflections because we've got one equation, two unknowns. Okay, so it seems like I've introduced this really cool new method that really helps us. In fact, there's also one further example that we can't get yet. Let me see if I can find this problem. I need to just get a screenshot of my problem. So let me find this. So we had two things that we couldn't solve using work energy methods. We couldn't get, for example, we couldn't use the force method where we didn't have a force directly along one of those axes, so we couldn't get that. We couldn't use it where we've got more than one displacement to determine. And then the problem that we're going to ultimately try and solve as a good example of work energy methods and how we solve for deflections and use the force method is going to be this dirty great structure here. Okay, so I'm going to say that we're going to choose one of these reactions as being redundant. This structure here, we've got an external load and we've got four reaction forces. I've got this one, this one, this one, and this one. So I'm going to say we're going to get rid of one of these, and we can't easily determine the displacement along any of these using either the simple sort of geometric methods, and we also certainly can't use the virtual work method, the work energy principle as we've described it. The answer to all of these is the principle of virtual work, and it's such a powerful observation in physics that it's just wonderful. And I'm going to go through it, and I'll go through the theory in the rest of this lecture. Hopefully you'll be as amazed as I am and you'll think, yeah, man, that's amazing. And then we'll go through some examples and you think, that's amazing, even further. And you'll write to me and you'll think, yeah, that's amazing. I'm so glad, I'm so alive through understanding this wonder of physics. It's wishful thinking, but let's go through the principle of virtual work. The solution to both of those problems is, let's just make a force up. So the solution to both of those pitfalls with work energy methods I was going to put arbitrary and infinitesimal. Since it's arbitrary, we don't need to say that it's infinitesimal. We can just say, let's invent an arbitrary force. This will be our virtual force. Okay, so we apply a virtual force to the structure. Doesn't show us yet how we can solve for anything, but all will become clear. The fundamental tenet of how work energy principles work, of how virtual work works, is it's the same as work energy principles, but the reason it's really hard to describe this without saying work. The reason that these methods can be applied, the reason that virtual work can be applied, is that a force does not have to directly cause a displacement in order to do work. Okay, a force does not have to directly cause a displacement to actually do work. And what do I mean by that? Well, let's imagine we've got a structure. Okay, we've got super amazing imagination, so when we imagine our structure, we're just going to draw the exact same one that we've drawn every time before, because it helps us. So let's draw our structure. And let's say, for the sake of argument, we know the relationship between external forces and internal forces for this structure. Again, we would just go through the free body diagram and the method of joints. We'd have to use the force method for a structure like this, or in fact we could use the simple method we used last time, which was just the extension of this member. But let's say that we know the relationship between external forcing and internal forcing. And what I'm going to do is before I put any load on this structure, I'm going to apply a very small, arbitrary virtual force here. My virtual force, and it's virtual because it's got a superscript asterisk here. Okay, so that's going to cause the structure to move a very, very, very small amount. Okay, a very small amount that takes it to somewhere so close to the original position that I don't need to redraw these members. And we can say this associated tiny virtual displacement is delta asterisk as well. So let's think about what that looks like. If I draw a graph of my displacement and my applied force, just keeping an eye on the time. I'm supposed to see you guys in a review in about 10 minutes. I might have to drop you a message and just let you know I'll be 5 or 6 minutes late. In fact, let me just do that now. Okay, so if we have got this force and we've applied it at time, let's say at time t0, we've got nothing applied to the structure. At time t equals 0, we don't have this applied. At time t equals 1, we're not really thinking in terms of time in this. I'm just trying to get you guys to think about the sequence we're applying these forces. We're not going to do any sort of time-varying displacements. This is just a means to construct the problem. So at times t equals 1, we apply F star. Now that's going to cause, if this is my virtual force here, it's going to cause this virtual displacement, which we call delta star here. And I'm going to color this in. This is the work done by the virtual force through the virtual displacement, and this is equal to a half F asterisk delta asterisk. Color this in, written this down. We actually never use this. This is not the important part, and it's not the cool part. Let's now subsequently, at time t equals 2, some arbitrary time later, doesn't matter what these times are. Again, we're not looking at the times, we're just saying that this virtual force is applied first. We're then going to put a real force on. Okay, this is the real loading. It could be 150 kilonewtons if it was our original problem, but it's a real force. So the first one is our virtual force, the second one is our real force. So that takes us up to here. This is going to be F star plus F, or F asterisk plus F. We've got a linear structure that's going to take my line to up here. And it means that the total displacement is going to be asterisk star plus whatever the actual displacement of the structure would be. And then here, let's draw that on. Again, this one's so small that I don't even really need to draw on the structure, but let's say this one here is my real displacement. So let's colour these in. I've got this shape in here. This shape in here is the work done by the external force that we've applied, that F, the real one, when we move it through this second displacement here. So this length in here is the real displacement. This height here is the real force. This shaded blue area is our real external work done, half F multiplied by delta. But there's this second area, or the third area underneath here, which we're going to colour in green for now. And this bit under here is the key to understanding virtual work methods. So this area under here is the work done by the virtual force when it's been moved through displacement that's been done by the real force. I say it's the key to understanding virtual work. This area is the virtual work. So unfortunately I've used all of my colours. Let's see if I've got anything new I can use. Let's try, purple's a good colour. Okay, so our external virtual work is equal to, well, there's no half in it, it's equal to the real displacement multiplied by the virtual force. And let's remember, this is the thing that we're often trying to solve for. We want to know what the real displacement is of a structure. So why does this help us? Well, we've applied this external virtual force of 1. Okay? The principle that's going to help us is that the external virtual work also has to be equal to the internal virtual work. So the external virtual work is equal to the internal virtual work. So for a force that we've applied, UE star is equal to UI star. Then we've defined what this is. We've said this was equal to external virtual forces, F star, multiplied by, what colour did I use for real displacements? There we go. Multiplied by that, which is the real displacements. It's going to be equal to the internal virtual work. And we haven't described what that is, but let's just go through it quickly. It's going to be equal to the sum over m members of the internal virtual forces multiplied by the real internal extensions. Now let's think about what these mean. If we've done the method of free body diagram and method of joints, we know the relationship between external forces and internal forces. So that means that this external virtual force, which is just a symbol, could be 1, but it's just a symbol, means we can then define all of the internal forces as a function of the applied force, including just a force that's virtual and arbitrary. So the internal forces are a function of the external forces, and as a consequence the internal virtual forces are a function of the external virtual forces. Okay, so the internal virtual force is a function of the external virtual force, and we get that through having the relationship between those two things, which is the free body diagram and the method of joints. What are these on here? Well, this is the real extensions of each internal member when we apply the real load. Student is asking me how to join Zoom. That's fun. Real. So these ones here would be the. Let's not use purple because I've tried to keep that for talking about virtual stuff. Let's just use another color to highlight things. So these internal extensions are going to be however much each member extends or shrinks by due to that real load. So in this problem here, what we're going to end up with, we're going to end up with a bunch of expressions for these forces as a function of the external virtual force. So we can do it either all algebraically, or because we said this was arbitrary, we can just set this equal to 1. And we're going to end up with a bunch of numbers according to this. And what I hopefully think you'll end up seeing here is that our external deflection, which is the bit we want to know, is going to be equal to the sum of the internal virtual work divided by our external virtual force. And if we've called our external virtual force 1, it's pretty easy to divide by 1. It's just going to be equal to the sum of the internal virtual energy, because dividing by 1 is pretty easy. Okay, so that in a nutshell is the principle of virtual work. We apply some arbitrary placeholder forces to our structure. We let them be carried through the real displacements. That creates external and internal virtual work, and those two have to be equal to each other. And let's pick a nice and easy value. Let's say this is equal to 1. Okay? It's also very handy to make it equal to 1, because when we're using the force method for the first displacement, we set this equal to 1. We'll often just, for the force method, set the second force to work out the second displacement to be -1. So when we'll do the computations for this, you'll often see that the answers for the internal forces are just the minus symbol, sorry, the minus value of whatever they were for using the virtual work method. So this, in a nutshell, is the principle of virtual displacements. Why does it help us? Well, let's go back to this problem here. We can set this problem up. We can go through free body diagram, method of joints. We've got the relationship between external forces and internal forces. We can determine all of the real internal extensions, the DLs, due to whatever P1 and P2 happen to be, 150 newtons, 300 kilonewtons, whatever they are. We can then say separately, P1. Let's make that a virtual force. And let's, as a consequence, say that P2 is equal to nothing. So if P1 is equal to a virtual force of 1 Newton, let's work out what all of the internal forces just due to that 1 Newton are. And then got a list of those virtual forces, and we then multiply them by whatever the extensions were due to both of these. Add all those numbers up, and that's going to be equal to whatever the displacement is, delta 1. Do the same with P2. Set P2 equal to 1 and P1 equal to 0. We're going to end up with a bunch of numbers for our internal forces. We then go back to the list where we had all of the DLs for P1 equal to 200 newtons, P2 equal to 300 kilonewtons, whatever I said. Take those extensions and multiply them by the internal virtual forces when this was 1 and this was 0. Add them all up, and that is the delta 2 there. That is amazing. That is such a powerful and wonderful observation that was made in physics of solids. That's tremendous, okay? It'll start to make more sense when we go through more complicated examples, and the way I want to go next week is do a simple example and then do a more complicated example. And what I want you guys to do is make sure you go through them on your own. So there's going to be, I'm going to skip over parts like the free body diagram, method of joints. I'll release those again like later videos because you might need a bit of practice and you probably want to see how they're done, but you need to be able to do these bits on your own, okay? And getting caught up in the details of things that you should know, like the free body diagram, like the method of joints, doesn't help you think about this structure of what the force method is, what virtual work is, okay? So if you've got to this point, this is where you should be before Monday. Monday the, whatever it is, Monday the, is it the 29th? Yeah. So you need to be to this point by Monday. I'll tell you this in the review that you're all in now. I want you to, if you've got to this point, drop me a private direct message on Slack. Tell me what you think the virtual work will be useful for, what the principle of virtual work is. Just a little sentence saying, I watched these lectures and I understood this. I didn't understand this. I'm excited by this, I'm pissed off by this, okay? I want to see where you're at. Please send me that message. Please just do this if you've watched this. Don't warn other classmates if they happen not to have watched this far, okay? I want to see who's watching these lectures. So please go ahead and do that. Like and subscribe, and I will see you guys all in the meeting that you're all currently in, okay? Have a wonderful weekend. Watch the rugby. I'll see you all soon. Take care.